We now demonstrate how entropy effects can be used to separate the isomers of hexane. Now, hexane isomers consist of normal hexane with an octane number of 30, 2-methylpentane with a research octane number of 74.5, 3-methylpentane with an octane number of 75.5, 2,2-dimethylbutane with an octane number of 94, and 2,3-dimethylbutane with an octane number of 105. For incorporation into the gasoline pool, the di-branched isomers 2,2-DMB and 2,3-DMB are the preferred components. And typically, in an alkane isomerization process for octane enhancement, the feed mixture is isomerized using a modernite catalyst to produce a mixture of the hexane isomers that has to be separated into two fractions. The first fraction consisting of normal hexane, 2-methylpentane and 3-methylpentane that is recycled back to the isomerization reactor, whereas the di-branched isomers 2,2-DMB and 2,3-DMB can be recovered for incorporation into the gasoline pool. The question is, which adsorbent to use and what is the separation mechanism? Let us examine the use of modernite for separation of hexane isomers. Modernite consists of 1D channels that are 7 angstrom in this direction and 6.5 angstrom in this direction. The 1D channels are connected to side pockets that have dimensions 4.8 and 3.4. The side pockets are unable to locate the hexane isomers. The hexane isomers are normally to be found along the straight 1D channels. And let's have a look at the animations for normal hexane conformations and 2,2-dimethylbutane. You will note that 2,2-dimethylbutane has a smaller footprint, and therefore at saturation it is possible to locate more of the 2,2-dimethylbutane within the 1D channels than normal hexane that has a longer footprint. In principle, it is possible, therefore, to separate the isomers of hexane exploiting on the entropy effects due to differences in the molecular footprints. By sampling several thousand conformations of each of the hexane isomers, it is possible to construct a probability distribution of the lengths of the footprints for normal hexane, 2-methylpentane, and 2,2-dimethylbutane. 2,2-dimethylbutane has the shortest footprint, say about 2.8 angstrom. 2-methylpentane has a footprint on average of 4.5 angstrom, and the normal hexane footprint on average is larger, which is about 5.5. Molecular simulations of the unary isotherms are shown here for normal hexane, 2-methylpentane, and 2,2-dimethylbutane, and you will note that at saturation, the loading of 2,2-dimethylbutane is higher than that of 2-methylpentane, and the loading of 2-methylpentane is higher than that of normal hexane. The saturation loadings are the inverse of the footprints of the corresponding isomers. In order to demonstrate the exploitation of differences in molecular footprints to effect separations of hexane isomers, configurational bias Monte Carlo simulations were conducted for a binary mixture of normal hexane and 2,2-dimethylbutane, in which the partial fugacities of the two components are maintained equal to each other. The component loadings determined from CBMC simulations are plotted against the total mixture fugacity. We note that in the Henry regime, the component loadings are practically identical to each other, up to a fugacity of about 3 times 10 to the 4 pascals. But as the occupancy within the 1D channels of mordanite increases, the adsorption becomes increasingly in favor of the dibranched isomer at the expense of normal hexane that has a longer footprint and a lower packing efficiency within the 1D channels. The continuous solid lines are the IAST calculations of mixture adsorption using the unary isotherm data for the two components. A different way to explain entropy effects is to plot the adsorbed phase mole fraction of 2,2-DMB as a function of the mixture occupancy within the 12-ring 1D channels. The red circles represent the CFZ data calculated from the mixture adsorption equilibrium. The black line is the entropy maximization curve determined from the Boltzmann equation. S is equal to K, L, and W, where W is the Wahrscheinlichkeit, and the formula for which was described earlier in this presentation. We note that the maximum S curve qualitatively agrees with the Monte Carlo simulations of mixture adsorption equilibrium. The small differences between the maximum S curve and the CBMC data is due to the small differences in the binding energies. If we take the differences in the binding energies into account and determine the curve that describes the minimization of the free energy, that's the blue curve, we get nearly quantitative agreement between the minimum free energy curve and the mixture adsorption equilibrium determined from molecular simulations. The message to be drawn from this example is that the mixture adsorption equilibrium for hexane isomers in mordanite is almost entirely driven by entropy effects that are engendered by differences in molecular footprints. This is a computational snapshot of the conformations of normal hexane, 2,2-dimethylbutane, and 2-methyl pentane within the 12-ring channels of AFI zeolite that has dimensions of approximately 7.3 angstrom. Normal hexane has the longest footprint. The di-branched 2,2-DMB has the shortest footprint, and 2-methyl pentane has a footprint that is intermediate in length. Monte Carlo simulations for ternary mixtures of normal hexane, 2-methyl pentane, and 2,2-dimethyl butane are shown in this graph, and the hierarchy of loadings as post-saturation is approached is in decreasing order of the molecular footprint. And therefore, entropy effects can be exploited to separate hexane isomers using AFI zeolite.